One-dimensional lattice of carbon nuclei. Consider a one-dimensional lattice of carbon nuclei with interatomic spacing d is equal to 0.5 nanometers. The potential energy of one nucleus due to electrostatic interaction with its two nearest neighbors is B of x is equal to q squared over 4 pi epsilon 0, 1 over d minus x plus 1 over d plus x, where q is equal to 6e is the charge of each carbon nucleus and x is its position relative to its equilibrium position. Part A, sketch the potential between x equals minus d and x equals plus d. So let's rewrite this potential. That's when we have 3 carbon atoms with nucleus charge plus 6e separated by a distance d from each other in one dimension. The potential is given by this expression, kq squared over d minus x plus d plus x, when this moves a distance x to the right, let's say. So this would be d minus x, this would be d plus x. Now when x is equal to 0, we have q squared over 4 pi epsilon 0, where q is 6e, remember, 1 over d plus 1 over d. That's for the equilibrium position, which is equal to q squared divided by 2 pi epsilon 0 d. And on the other hand, if I look at the derivative of the potential with respect to x, dv dx, it is plus 1 over d minus x squared minus 1 over d plus x squared times this term, which is q squared over 4 pi epsilon 0, is equal to 0, but I can get rid of that term and say that this must be equal to 0. Okay. Why should this be equal to 0? Because that's the equilibrium configuration. That's where the potential must have an extremum point, the minimum. So we find that d minus x squared must be equal to d plus x squared. Therefore, x equals to 0 is a solution, is an extremum point. That's the equilibrium point. And how about the potential at x equals plus or minus d? The potential becomes, if I substitute x equals d here, this is going to blow up. So the potential is going to become infinite. So with these observations, I can plot the potential between x equals minus d and x equals plus d. So here is my potential b of x. There is an extremum at x equals 0, that's the minimum. So if I substitute x equals 0 here, this is what I find, that's the minimum potential energy. So that's equal to q squared over 2 pi epsilon 0 d, that's this value here. And it blows up at x equals minus d and x equals plus d. Therefore, this is the potential as a function of distance x, that where x is the position relative to the equilibrium position of the atom in the middle. Now, part B, at low energy, the nucleus remains near its equilibrium position at x equals 0, and the potential energy is well approximated as a harmonic oscillator. Use a power series expansion to write the potential as a quadratic function in x, dropping contributions at higher order in x over d. Now, if I stay close enough to the equilibrium position, the problem mentions that this is a harmonic oscillator potential. So let's see that here. The potential V of x is equal to q squared over 4 pi epsilon 0, 1 over d minus x plus 1 over d plus x. And now I can also rewrite this as V of x is equal to q squared over 4 pi epsilon 0 d plus x plus d minus x, writing this with the common denominator, d minus x times d plus x, that's d squared minus x squared. You can see that plus x and minus x disappear. And this is going to give me, because I have 2d here, this is going to become 2. So q squared d divided by 2 pi epsilon 0. And then I'm going to write the remaining with the 1 over d squared parentheses 1 minus 1 over 1 minus x squared divided by d squared. All right. Now the potential as a function of x is then q squared over 2 pi epsilon 0 d, because I have this d making the bottom one d squared d. Then I have 1 minus x squared over d squared to the power minus 1, where I have x much less than d. We're staying very close to the equilibrium position. And I recall that 1 plus z to the power n is approximately equal to 1 plus nz when z is much less than 1. So this is what I recall from the Taylor series expansion, which we use very frequently in physics. Okay, so that allows me to write approximate potential V of x to be q squared over 2 pi epsilon 0 d 1 plus x squared divided by d squared. And I also recall that q is equal to 6e. So with that, the potential function takes the following form. I'm substituting for q 6 here. 6 times 6, 36 divided by 2 is 18. So I have 18 e squared divided by pi epsilon 0 d 1 plus x squared divided by d squared. So it is a quadratic function of the deviation from the equilibrium position. As mentioned in the problem statement, it is well approximated as a harmonic oscillator. V of x can be written as a quadratic function in x. Part C, well, if we do that, what is the spring constant K prime? All right, so the potential V of x has a constant term V0 And then it has this form, 1 over 2 k prime x squared. All right. So that's the harmonic oscillator potential, 1 over 2 k prime x squared here is equal to 18 e squared, 18 e squared over pi epsilon 0 d cube x squared. So that's this term here. It's multiplied by x squared over d squared. So from this expression, I can recognize k prime. K prime is equal to, multiply this by 2, 36 e squared divided by pi epsilon 0 d cube. So that's our k prime. Well, we can find the numerical value. Epsilon 0 permittivity of free space is 8.854 times 10 to minus 12 farads per meter. So k prime is 36 e squared, 36 times 1.6 10 to minus 19 coulombs squared divided by pi epsilon 0 8.854 10 to minus 12. The next term is d cube. So we have 0.5 nanometers, 0.5 times 10 to minus 9 cube. So this gives us a k prime value of 265 newtons per meter. All right. So we have shown that for a one-dimensional chain of carbon atoms separated by a distance d, the potential can be written as kq squared 1 over d minus x plus 1 over d plus x when this atom moves a distance x to the right. The distance between these two becomes d minus x, between these two becomes d plus x. That's the potential. Now this potential we can sketch and find that when x is minus d and x is plus d, it blows up. It has a minimum at x equals to 0. Its derivative is equal to 0 at x is equal to 0. And with that, we can plot the potential as a function of x like this. And in part B, we want to show that it can be approximated as a harmonic potential by using power series. That is to say, the potential can be written as a quadratic function in x for x much less than d for small deviations. And here, if we manipulate this a little bit, we find that it can be written in this form. And when x over d is much less than 1, this term is very small, so it can be written as 1 plus minus 1 times minus x squared over d squared. So it's 1 plus x squared over d squared. So we have this quadratic term that we are after. The potential that has the quadratic term here is 18 e squared over pi epsilon 0 d cube x squared is 1/2 k prime x squared. That's the potential energy for the harmonic oscillator. And so if these two are equal, we can see k prime should be given by this. And with that, if we plug in the numbers for a separation of 0.5 nanometers for d is equal to 0.5 nanometers, we can even calculate this spring constant to be 265 newtons per meter.